Andrew is our XRF applications engineer. He's our senior specialist specifically for the XRF Orbis product line, which is the Micro-XRF micro-focus X-ray tube. He'll go into the benefits of XRF and also some comparisons with EDS. And from there, we'll then go into some sample analysis comparing data between the XRF and the SEM.
Good afternoon. Thanks for joining us. So as Tara said, we're going to be looking at some of the comparisons between EDS and Micro-XRF, which we kind of give as a complementary tool to each other. So the two closest techniques to Micro-XRF would be bulk XRF and EDS, actually. So if you're familiar with either of those two techniques, they're very similar. With relation to bulk XRF, we use the same physics. An X-ray tube generates our source for an X-ray beam, which is then generally collimated or focused to a relatively large spot size in the millimeter scale. And so the analytical depth and area tends to be larger, and the sensitivity is very good for high Z elements. But there's no stage scanning. It's generally just a simple sample changer kind of thing. Whereas EDS has obviously the scanning capability, but it uses an electron beam, which tends to have very shallow penetration and a very, very narrow analytical area. Also requires images from an SEM, which is a separate unit. And so Micro-XRF kind of lies in between those two techniques, where we utilize the bulk XRF kind of information, but we incorporate scanning features such as an XYZ stage, a much smaller spot size so that we can get images and distributions and line scans and things like that. Some of the advantages to the technique kind of common to Micro-XRF. For one thing, it's non-destructive. It's very important. The sample preparation involved is much lower. It's more tolerant of samples that have varying topography. So mounting and polishing is generally not required. Conductivity is not an issue, so it doesn't have to be coated. And as I said, the sample shape and height can be irregular, more so than EDS. The sensitivity will improve as you increase the atomic number, and generally we get down to less than 100 parts per million for those kinds of elements. However, we do start sensitivity at sodium, and we don't see any of those organic elements, which we will see in the example. We could also operate in low vacuum or air, so some samples that you don't want to pull vacuum on can be run in XRF, particularly if you're looking for trace elements that might be heavier. Metals, for instance, in a liquid is a good example. It's more appropriate for larger scale features, as I mentioned, due to the larger spot size and the larger stage. You tend to map larger areas much faster, so areas that would take you days or weeks with EDS would generally take much faster with Micro-XRF, but you have a larger spot, so the resolution is a bit poorer with Micro-XRF. The X-rays, as I mentioned, are more penetrating, so sometimes they can even go millimeters into your sample, which gives you a more depth profile than just the surface chemistry. And also the imaging is done via optical cameras, which are integrated into the unit and not a second imaging unit, so that's a convenience factor. EDS, some of the advantages here is it's better for the light elements or organic elements, carbon and hydrogen and so forth. And even for elements like sodium and silicon, which we can still detect, sensitivity tends to be better with EDS. So it depends on what you're looking for in your sample. In addition to the fact that the size of the sample is very important to consider. Obviously, it's a much smaller spot size, and the scale of the features that you'll be seeing is much smaller. So that's another factor. The weaker beam penetration could be an advantage. You might not want to see what's underneath. If you have a 30-micron cross-section of a geological sample, XRF will get the glass signal from the actual mount. So with EDS, you're not going to get that. It's going to get just the cross-section itself. And of course, there are some sample preparation factors that you have to potentially go through. And you typically run, well, you run either in vacuum or variable pressure, so just liquids and any hydrated samples would not be doable. And you have a separate imaging system as well. So one factor that we mentioned is sample preparation, and one of the things that, the big difference is between XRF and EDS is this. You get samples in, and with micro-XRF, you have a lot of the times the luxury of just putting it in and running it immediately and saving the time and resources of prepping the sample. With EDS, whereas you might have to grind, polish, mount, cross-section, or coat your sample in any combination, with XRF you could take those same samples and run a quick scan on it and potentially eliminate the further need for EDS analysis. These are just a couple examples of how we mount samples for analysis on XRF if the sample is not thick enough for a bulk sample to basically absorb all the X-rays. We can elevate them above the stage and kind of eliminate some of that scatter we would normally get from the stage top. And so one method is double-sided tape, or another one is just Mylar film in a sample cup with a clamp around it. That elevates it above the stage, eliminates scatter, and pretty much, tries to optimize the signal from the sample alone. So that's optimal for thinner samples, particulates, fibers, powders, and so forth. Another thing that's been mentioned is the sensitivity. The sensitivity from micro-XRF, as you can see, leans heavily towards the higher energy elements, and EDS leans heavier towards, it's better performance for the lighter elements. Here we have a glass standard that we collected at 20 kV for both techniques, and you can just see the spectrum overlay. The silicon peak is where they were both normalized, so that's purple. But the red spectrum that you see is the EDS, and the blue spectrum is the micro-XRF. So in the earlier part of the spectrum, you see carbon, oxygen, sodium, magnesium, aluminum coming in very strong with EDS. They start to kind of even out at a certain point, and then beyond that point, you're seeing elements with micro-XRF that you don't detect with an electron beam, like chrome, manganese, and iron. And sorry, that's covering that little top a little bit, but the sensitivities or the detection limits for each technique for micro-XRF and for EDS are shown for some of those elements from titanium to lead. And as you see, it gets better as you increase the atomic number with XRF. One thing about XRF is you do pick up the tube scatter lines, so whatever anode material your tube has, you will get that line in your spectrum generally if you don't filter that out. So in this case we had a rhodium tube, and that's going to be an artifact peak that you see in your resultant spectrum. So that's one thing you don't have to deal with on the EDS side is those. So adding to the sensitivity issue is the fact that micro-XRF is actually starting, as we increase atomic number, we start to just use the K lines as opposed to reverting to the lower L lines. So in the instance of, for example, strontium, zirconium, silver, normally with EDS you would probably use those L lines to detect if it's present. And with micro-XRF, typically we have a tube that goes up to about 50 kV. The Orbis, that's the tube that we have on the Orbis. And that is capable of analyzing K lines for those elements, and that eliminates a lot of potential confusion. If there's an overlap with the L lines, you have the option of looking at the K lines to confirm whether it's present or not. So we'll take a look at that in the example in a later slide. And in addition, you can use primary beam filters with micro-XRF, which allows you to increase or optimize the sensitivity even further than you would normally get without it. And that's not an option, obviously, with an electron beam. Again, however, we do start at the sodium, so that's anything before that will not be seen. So spectral mapping is mentioned here because this is mainly the primary form of data that we're going to be using for our example. And here the concept is same for both EDS and XRF. We collect a series of points in a matrix style, and we store that data in an array and correlates the data to that stage position, and we get a distribution image. And normally we can then recollect the actual spectral data by summing up a series of points, and then we can verify if that element is present or not. So we can map as pure elements or oxides. CPS maps or quantitative maps in weight percent is available. That's pretty standard stuff. However, EDS then has the ability to do phase mapping, which is not something that we can do with XRF. So you can potentially, depending on your sample, get more information having that capability with EDS. Pure elements, we could do overlays, we could do RGB kind of merges. But we don't really have the true phase map capability that you have with EDS. Nor can we map on the small scale that you get with EDS either. So that's depends on what area you're trying to look at. In this example, we have a circuit chip that's been mounted, and we have a nice flat surface, a lead-free solder, so we can also confirm if there is or is not lead. And again, so if we got the circuit chip for Micro-XRF, we'd normally just be able to put it into the chamber and run it and analyze it, and that's it. But having it prepped for EDS was not really necessary, but to run it, obviously we had to run it with both techniques, we mounted it. And for the Micro-XRF conditions, we have 45 kV in a rhodium tube, 500 microamps, using a 30 micron polycapillary. And so we mapped a area that was roughly 36.1 by 7.2 millimeters. The image you see on the top is the original color image of that analysis area. That's the area that we mapped, and that was kind of a stitched field map using the video cameras on the Orbis. And so some of the elements that you would expect to see on a sample like this are gold, copper, tin, silicon, and various other elements like that. And some of the interesting things about the results, for instance with gold, is that we can map for gold L and gold M. We could add both series of lines for the spectral maps. And as we were saying before, they both have different escape potentials, and so you get different information from getting to use both lines. The gold L line would probably be too high for EDS, and normally you probably get the M line, which is more representative of the surface. Whereas the L line here, although it's blue and not the greatest color, the L line comes from a greater depth underneath the surface, and therefore you see what's more representative of subsurface presence of gold. Sometimes the L line and K line are not really all that different, which is probably telling you that throughout the depth of the sample, it doesn't really change in distribution or area. And that's pretty much what we see with the tin L and the tin K, pretty much, exclusively in those kind of hot spots there, although we do see a little bit of extra tin in some areas, mostly similar. We have barium L and copper K, and just added some additional elements to fill in the rest of the picture, basically. But last 4 elements here: phosphorus, sulfur, silicon, aluminum. Again, lighter elements that probably come through better on EDS, but we could still see them if, it's still not an issue to see them. However, as you get lower and lower in concentration, it does become more difficult. So, but this is, mapping for aluminum, for instance, is very doable to about a couple thousand parts per million. And so from the map of that chip, you basically can add up all the points for a summation of that area. And then you could also take a max channel spectrum, which basically just isolates the highest intensities throughout the various channels for each point. Basically just showing that, yes, we can confirm that there's no lead present in that chip. Integrating the hardware together for both EDS and XRF, it is possible to do, and there are some issues with that. Yes, we're saying the data complements each other very well. However, if you start to integrate the two hardware together, you face an issue with, for one, sample type. If you can't pull vacuum on your sample, whether it's wet or it will degas, you can't run it on that system, period, due to the fact that you have an EDS chamber, obviously, that needs to be evacuated. Sample preparation, you no longer have the advantage with Micro-XRF being an easy sample prep technique. If you're going to put it into a dual system chamber, you then automatically just have to prep all your samples the way you normally would for EDS. So the benefit is lost on the micro-XRF side. Also, there's alignment of both of the beams, the electron beam and the X-ray beam, and getting them to correlate on the exact same areas is generally easier said than done. And between those two beams, the XRF beam will have to be an oblique beam coming in at an angle, and that can bring up some topographical issues. The beam can elongate as you're coming in at an oblique angle, as opposed to a standalone unit where we have this beam coming in perpendicular to your sample, and the beam doesn't distort as you start coming in at an angle. Also, the XRF would be limited to one spot size probably, and we do have an option to select up to 3 different spot sizes. So presumably that capability would be lost if you integrated the two. So yeah, there's some hurdles to overcome on that side, both from the sample side and the hardware side, but definitely not out of the question. So I was going to give it to Tara, who's going to run the same sample basically on EDS and describe what we get with those results.
So with EDS, we're uncovering a slightly different aspect to the elemental information that we get from a material. In this case, as Andrew described, it's a cross-section of a solder sample. Originally, this sample was used for EBSD analysis to look at the microstructure using EBSD, and we have been able to correlate the diffusivity of different materials, different elements, based on different orientations of the solder. Now with EDS, we take a look at the materials, what elements are present, and when we do phase map, we correlate the elements together and combinations of elements together. So where there are cases single elements, and sometimes you have oxides and combinations of elements together. Of course, the other advantage is the low energy, or the low energy X-rays light element analysis. So for areas of the epoxy or the carbon oxygen containing areas, oxidized areas can all be uncovered with EDS. So I'll be turning my backs to you, but please feel free to focus on the monitor as I start doing some of the data collection within the software. We've got this sample running live in the microscope, and we'll just bring up the image here on the screen, as you can see. So with SEM EDS, we're limited to higher magnifications compared to the XRF, where you could cover large areas. The advantage with SEM EDS is that you can get higher magnifications and look at site-specific areas that might not be possible to resolve with optical and XRF. We could activate survey mode for the detector and quickly collect our data from a number of points to understand the chemistry and the distribution of elements through the material. And very quickly, we get our first area and results. And then as we sample around, we could show how those areas change. Also, in live time, we're able to even get concentrations and even some graphs representing the actual chemistry from those areas. As we change different areas, the spectrum updates in live time, as well as the quantitative and graphical results. Now, all of this, of course, is just surveying with EDS. And the next step would be to do a map to understand where the distribution is with EDS. So we then jump over to the mapping and start the map acquisition. And another possibility is also to do multi-field mapping or area analysis, where we could get several fields of view and automatically move the stage in between runs and stitch them all together. The result of a multi-field run would be similar to the XRF results, where you could scan large areas and get the elemental results, but still get the low energy analysis as well. Okay. Does anybody have any questions?
When you use a thin polymer window, do you get light element sensitivity? Because you said you had a beryllium window and then you had the polymer window. Does that improve the light elements in the XRF?
In the EDS. So in EDS, you'll be able to get the beryllium and higher, beryllium, boron, carbon, nitrogen.
Is this live imaging code, or is this micrograph?
This is live SEM imaging, and EDS, the data collection was in live time.
Because I noticed when you took acquisition from an area, the image didn't disappear.
Oh, right. No, the image stayed the same. We were just scanning from different subsets of areas. So each time I drew a new box on the image, that was collecting the spectral data only from that point, only from that box or that point or the area that I collected
Does the
from.
software, I guess, yeah, you said it stays for image drift, so it'll make sure it's still the same area.
We do, yeah. We have a drift capability, which especially at high magnifications or material that's beam sensitive or charging, moving around underneath a beam, drift correction is highly valuable to keep it in place.